Hello friends. In the previous lecture we considered how one can adopt the approximation approach that we have been looking into to handle data set. So if you consider a set of data involving a single independent variable, say x1, which gives us an output that is based on or that can be expressed as f of x1, and we have a set of such inputs and a corresponding set of outputs. Now, we saw that it is possible for us to find the derivative of these individual data points, the first derivative, so on and so forth, using the approximation techniques that we have been looking into thus far. Now, one of the critical aspects that allowed us to focus on using the approximation techniques in handling the data set is that these data sets, while we attempt to find the derivative for these data sets, they present us with a problem, they present us with a bottleneck. That is, even though the central different approach can be adopted for most of the data set, the central different approach with its error of the order of delta x square can be adopted for most of these data points. It cannot be adopted for the first and the last data point. So it means we have rather inconsistency in the approach that we are adopting, and correspondingly an inconsistency in the amount of error associated with it and the order of error associated with it, or to put it simply, the accuracy of our derivation. Now therefore we are forced to use forward difference in case of the initial data points and backward difference in case of the final data points. Now in our previous lecture we saw that even though we are forced to use forward difference and backward difference for certain data points, it is possible for us to improve the accuracy of the approximation and bring it to second order accurate. Meaning it is possible for us to formulate the forward different expression, the approximation, in such a way that the error associated with it is of the order of delta x square, both forward difference and backward difference. Originally, the error associated with these approximations are rather of the order of delta x. So what essentially we are doing is we are minimizing the error by an order. Now how we were able to do it is, instead of considering the immediate point alone, we considered the point, 2 points or 2 immediate points. In the same way, in case of the backward difference, instead of considering just, so if our starting point is the point xn, instead of considering just xn minus 1, we also consider xn minus 2. So what essentially then we would have is, we would have f of x, then f of x plus delta x, and f of x plus 2 delta x. So now by considering, instead of just considering f of x and f of x plus delta x, by including another point, we were able to improve the accuracy of our approximation by an order. In the same way, if we consider the last point, instead of considering f of x, if we include f of x minus delta x, so this would be 1, f of x 1, and this would be f of xn, and f of x minus 2 delta x. By considering an additional point, we were also able to improve the accuracy associated with the backward difference approximation. Now we also saw that it is not for us to expect that the difference between these individual data points are of the same width, or these individual points are spaced in such a way that they are uniform in nature, they are regularly spaced, that is, the distance between the x1 and x2 is the same. So in that case, what we essentially need to do is replace delta x with xn plus 1 minus xn. So all we need to consider is the subsequent point to that of the existing point, consider its difference, then we would be able to estimate our delta x. So correspondingly the delta x can be replaced, and therefore it is not required that all these data points that we are considering are separated by the same width. Now the question still remains, why would one want to find the derivative of the data points? Of course there are data points, and maybe in the subsequent modules we will find a ways to develop predictive models for handling this data points from this data point, so that when you feed an input, you are able to predict. So when you feed an input that is not included in the known data points, you are able to estimate an output. So it is possible for us to develop a predictive model. So that is what we will be looking into in subsequent lectures. We will attempt to develop a predictive model from a given set of data points. So that is something that we could relate with. So often when we do experiments, we want to selectively do some experiments and develop a predictive knowledge. So therefore developing a predictive model from a given set of data is something that we can relate to. But why do one want to rather find the derivative of a set of points? Now, one way of justifying this, the need for finding the derivative of the data points, can be rather captured by considering one of a real life research that people have been performing till today. Now, as maybe you are very well aware of it, because that's the reason why you took this rather theoretical course, that as much as the computational resources are increasingly being available to us, as the cost of the computing machines gets reduced, we are allowed to use sufficient degree of computational resources. So it means that whatever experiments that we are performing in a laboratory setup using a physical machine, we are attempting to replicate it in a computational framework. So whatever research we are doing, say be it on phase transformation, be it on mechanical testing of materials, whatever research that we are performing in a laboratory setup, we are attempting to recreate it and also build on it in a computational framework. So there were days wherein all these computational or theoretical techniques were rather qualitative in nature. So they will not be material specific. All that this approach will talk about, or all that this approach will render, is a qualitative understanding of, a generalized understanding of what a behavior is. So when you have, supposing a phase transition, supposing there is a phase transformation, this qualitative model can tell us what is the mechanism behind this phase transformation that is happening. In a generalized case, irrespective of the material that we have, what is the phase transformation that is occurring? What is the reason behind the phase transformation? The theoretical model can tell us. So all it can say is, okay, this is the difference between the free energies, and that's the reason why there is a phase transformation. And even based on just the difference between the free energies, this model can predict the kinetics of the phase transformation. However, these techniques were largely qualitative in nature. So initially, when the theoretical techniques were introduced in the realm of material science, these were largely qualitative in nature, meaning they gave us generalized understanding. Now, from the generalized understanding, we need to extrapolate it and adapt to our laboratory setting to understand why what we observe is happening and how we can understand it. However, we are now moving towards quantitative modeling. So again, in the framework of the material research, particularly where these mathematical techniques that we are interested in, they are employed, is in the quantitative realm, meaning we no longer want to have a generalized understanding. We no longer want to model a generalized materials behavior, but we want to model specific materials behavior. We want to see how steel behaves in this particular temperature and what would be the rate of the phase transformation exhibited by steel. And not only just any steel, just mild carbon steel with iron and carbon. We want to have a sophisticated numerical techniques or sophisticated computational approaches that can help us understand what would be the phase transformation, what would be the behavior of the steel, which is just not comprising of iron and carbon, but it also include manganese, it also include chromium. So we want to be as quantitative as possible. So therefore, we are moving towards rather recreating what is happening in the physical world, the influence of the different alloying elements in the computational system using a computational device. We want to recreate it using in a computational framework using appropriate devices. Now, in order to do that, we need to have certain foundation. We need to extract certain foundation, certain knowledge, certain data from elsewhere. Now, how quantitative approaches are essentially being modeled is, you have a largely numerical model. You would have a largely numerical model, and this numerical model will focus on a given, or it will focus on modeling a given behavior. Supposing if you take an example of phase transformation, the model that you develop needs to be rather a generalized model. The efficient way of developing a model, it needs to be a generalized one, meaning it can be used for any material. Now, this is then pertains to the qualitative model. So when you want to model a specific material behavior, say the phase transformation exhibited by a specific titanium alloy, you would adapt a model. Now this model is generalized in nature. This is rather a qualitative model, because this model is versatile, of course, and it needs to be adapted to any material system. Because when you develop a model for a specific material and you keep on developing model for each and every specific material, that will not be an efficient way to go about. So what is usually done, the approach that is usually taken is you will develop a generalized model which can be adapted for any material system. Now, the quantitative aspect of this model comes by feeding in appropriate data. Let me repeat, the model itself is a generalized one, model itself is a qualitative one, but the quantitative aspect of this model is achieved by feeding in appropriate data. Now the appropriate data is rather fed in by using another totally a different technique. So if you consider again the phase transformation, now the phase transformation can be rather modeled by several different numerical techniques. You have rather you can use phase field modeling is one of the techniques, and you can also use rather cellular automata is being used recently nowadays to model microstructural evolution, and there is also Monte Carlo technique that can be adapted to model the microstructural evolutions. And in addition to that, you can have purely an analytical treatment that can help us predict the kinetics of, you can develop an analytical model, analytical framework that can help us predict the kinetics of a phase transformation. Now, these are rather generalized. When you consider just the framework of these models, just the outline of the models, these are just generalized models. These are just qualitative models. All you would find is a set of equations and how they are solved. The quantitative aspect comes from a different package. Often the quantitative aspect which tells us which particular material we are modeling, which particular material we are interested in, that aspect comes from a different package. Usually it comes from what we refer to as the CalFAD. So usually when you have a numerical model that you want to rather study a specific metallurgical behavior, a specific behavior that is associated with a particular alloy, you need to feed in the appropriate data, appropriate information, and this information usually comes from a different source. What essentially we do is, in order to make this model quantitative, we go to CalFAD, take the necessary information, and then feed it back to the model. So model as it is, the numerical model as it is a generalized one. It is a qualitative one. You make it quantitative by taking a different route, adopting or using a different package, taking the specific the required information from that, and then feeding it to the numerical model. Once you feed the quantitative information, the relevant information that is specific to a given alloy, then ultimately what you are doing is you are making your model quantitative one. So this is what the overall approach, the generalized approach that is often adopted to have or to quantitatively model a given behavior. There will be a generalized framework, there will be a numerical framework. You will feed in the appropriate data that you have often gathered from an external resource. This external resource is called the CalFAD. There is nothing but the calculation of phase diagram. I believe you already know that. So cal means calculation, phase and diagram is D. So calculation of phase diagram is what gives you CalFAD. So to make your model quantitative, to feed in the appropriate information, to make the model quantitative, you get it from CalFAD. Now what CalFAD does is, so the CalFAD provides us the relevant information that we are familiar with. So when you want to build a phase diagram, if you could recollect your courses on thermodynamics, the information that we need are often the free energy, the derivative of the free energy, or rather let me use concentration as the variable. So we have your free energy, and this concentration, it need not always be a binary system, meaning one independent concentration. So this concentration can be a number of concentration, meaning this can include any number of concentrations. And we also need the chemical potential of these individual concentrations. And we might need the second derivative, the derivative of the chemical potential, and of course, so those things are available in CalFAT framework. I mean, you need to use different packages. You have thermocalc, you have DTRA, so different packages can give you the information about these free energies and chemical potential pertaining to a given concentration. So these information, they are separately available in an external resource, and you have your numerical model. So generally what is done is, for the concentration, the free energy associated with the system would vary. So supposing you have a system, and in that system you are initializing a system with a given phase. So there is a matrix phase. So this one would be the matrix phase, and this is another phase. So this would be the matrix phase. So this would be another phase which is rather loosely referred to as the precipitate, even though it's not often precipitate. It is loosely referred to as precipitate because you have matrix and precipitate, but it can also be any other phase. Now what essentially, the way you would initialize the system is you would introduce the appropriate difference in the concentration that is reflective of the real life system. Supposing if you have a MC or FeCmn system, a manganese steel, the concentration of the matrix will be reflective of the phase that you are interested in. So the concentration of the matrix will have the specific composition associated with a given phase, and the precipitate will have a specific association with a given phase. The matrix can be austenite, the precipitate can be ferrite. Now, in order for us to model the phase transformation of such a system, we are now have a specific system that is a manganese steel, and we have a specific setup wherein we have a ferrite that is surrounded by austenite. Now what essentially we are attempting to do is we want to model the growth of ferrite within the matrix of austenite. Now for that, this in the physical world is rather governed by the free energy difference associated with the corresponding concentration of the precipitated matrix. So therefore, in order to model this, we need to introduce the information about the free energy and also the chemical potential. So what essentially would happen is, this precipitate, if the condition is appropriate, if the condition is that the precipitate needs to go, there needs to be a free energy difference. This free energy difference means the precipitate has a lower free energy when compared to the matrix. And in addition to that, the phase transformation means that there is a concentration difference, and this concentration difference needs to be rearranged in such a way that the precipitate is allowed to grow. The precipitate cannot directly, the growth of the precipitate means that the concentration of the matrix is changing, so that it now has the concentration that is identical to that of the precipitate. The concentration is getting redistributed in such a way that the entire matrix concentration is gradually getting replaced by the precipitate concentration, and this happens because of the difference in the chemical potential, because the chemical potential, the components, they have the tendency to move, they have the tendency to propagate in response to the chemical potential. The components, the chemical components, say it's carbon, say it's magnesium, what essentially they would do is they tend to move from a high potential region to a low potential region. So what we have is, we have phase transformation, and this phase transformation is rather governed by the redistribution of concentration. So even though the phase transformation is rather dictated by, it is introduced by the diffusion or difference in the free energy. So it's the difference in the free energy, delta F of C. Even though this is what governs or dictates the or introduces the phase transformation, the redistribution of the chemical components, the redistribution of carbon and manganese in the system is achieved by the first derivative of it, the difference in the first derivative of it, or the difference in the chemical potential, that is often represented by mu, which is again, it varies with carbon and manganese. So essentially, even though you have developed a generalized model for recreating or reproducing this phase transformation as an FeCmn system, you have a phase model that is capable of rather recreating or rather simulating the phase transformation. In order to make it quantitative, we need to introduce these free energy information, and we also need to introduce this chemical potential information. Now, if this is the case, if we want to introduce, or if these information are available in an external resource called CalFAT, what one can do is, for each and every time step, the numerical model can send out a signal to estimate the corresponding free energy and the chemical potential. What an approach that can be adopted is the numerical model, which is a generalized one, which is a qualitative one, can send out a signal to this external resource at each and every time step, can send out a signal to this CalFAD resource at each and every time step, saying that, okay, this is my distribution of concentration, what is the corresponding free energy and the chemical potential values. So for each and every time step, this distribution of concentration can be sent to the CalFAD, and the corresponding free energy and chemical potential values can be fed back into the model. So what essentially can be done is, in order to make your numerical model quantitative, you can at every time step, before calculating or before solving the equations, you can, to make it quantitative, you observe or you gather the information from the external resource. So this technique is rather a valid one even today. As of date, this is one of the state-of-the-art technique that is adopted to make the numerical model quantitative. That is, for each and every time step, there is a signal that is sent out to the external package, the relevant informations are gathered, and then it is sent back to the model and the equation is correspondingly solved. So this is one way of making your whole approach quantitative. Now, there is also another way of making this approach quantitative. Now, that approach involves handling the information before, or instead of feeding in the information simultaneously, there is another approach. Like, instead of feeding in for each and every time step, instead of having both the numerical model running and the external package running together and having the exchange of the information, instead of doing that, so what do you mean by exchange of information is, the numerical model, it feeds in the concentration distribution, and the corresponding free energies and the chemical potential is fed in by the external resource that deals with CalFAD. So this is one way of doing it, and like I said, this is currently being used in one of the well-known packages. It's better not to name it. Now, what other approach, rather a numerically approximated approach involves is, now what this CalFAD essentially gives us is rather data points. For a given concentration, it gives us a given free energy value and a given chemical potential value. So what it essentially gives us is a set of data points. When you have a domain, and you can rather discretize this domain, like split this domain into individual cells, and individual cells, they are associated with a specific concentration, say Ci. So the reason I introduced this vector notation is because it can be the concentration of carbon, or it can be the concentration of manganese. So what essentially we are doing is, we are feeding in the concentration of a specific cell, of specific discretized unit in the domain. So this is the simulation domain, into the CalFAD, and we are generating appropriate, or we are gathering or estimating the appropriate free energies and the chemical potential. So what it means is, for the cell 1, we are able to generate appropriate free energies and the appropriate chemical potential. For cell 2, we are able to generate the same, so on and so forth. Now, when you consider the nature of the free energy curves, the numerical nature of the chemical potential, when you look closely, what we often observe is, the free energy curves, they adapt a specific form. Particularly in the region of the phase transformation, all that we are interested is the phase transformation, and from our thermodynamics background, we can state that the free energy curves, the nature, the trend of the free energy curves, they follow a specific trend, particularly with relation to concentration, and this is usually of the form of a parabola. Now, even though schematically we represent the free energy and concentration relation in the form of a parabola in most of the thermodynamics textbooks, this is how it is being represented, even though it is often called as a schematic representation. When you use a CalFAD package, when you feed in different concentration, when you get the corresponding free energy, you will observe a similar trend of this form. So all that it means is, both qualitatively, both schematically, and also quantitatively. So whatever inspiration that we have for the schematic representation, it comes from the quantitative data that we have. So the quantitative data that we have also has a trend of this form. So essentially, now when there is a trend of this form, now if we are able to approximate this trend, so what this trend tells us is, this trend tells us how the free energy would vary when the concentration changes. Now, if we are able to approximate this trend, if we are able to, instead of handling or instead of rather gathering this information, that is concentration free energy information, as individual data points, if we are able to express it as a function, then all we can do is, what we can do is, we can replace this exchange of information. We can replace this exchange of information by including the function that we have developed. So plus the numerical model, and we can include the function that we have developed, the approximation that we have developed, and what we end up having is an all-inclusive model. Now this is also quantitative in nature, but essentially what we have is an all-inclusive model. Now what we have seen is, in order to make our approach, the numerical approach, quantitative, there are two ways for us to proceed. We can consider the information that we need as individual data points, then use this information exchange approach, that is run two packages parallelly, that is a numerical model parallelly and also the Calfan model parallelly rather, and then have the exchange of information and then make your model quantitative. That is one approach. The other approach is, we can rather replace these individual data points. That is essentially, when you have an exchange of information, what you gather is these data points. You can replace these data points with a function, and you can augment that function, you can append that function to the numerical model in such a way that whenever there is a concentration for which the free energy and the chemical potential is unknown, you can use this function to calculate the corresponding free energy and chemical potential. So therefore, essentially what we are doing is, we are making our approach computationally efficient. Of course, we are approximating a curve from the data point, but what we are essentially doing is, we are essentially avoiding having two different packages running simultaneously, avoiding the time taken for the exchange of information. We are doing all this, we are avoiding all this by augmenting or by including this approximated function within the model itself. So now, in order to translate these data points into a function, we use, or the derivative of these data points play a critical role. Let me repeat, the starting point of this particular discussion was that we want to know what is the relevance of finding the derivative of a given set of data points. Now we have come to a point wherein we see that the numerical approach can be made seemingly efficient by including or by translating a set of data points into a function, so that we no longer need an external resource. Now, in order to translate these data points into a function, we can use, or we need, the derivative of this data points. Now, of course, when you have a set of points, and from that you need to derive a function. Now there are numerous ways of doing it, and of course one can use machine learning technique to do that. But using machine learning technique for deriving a function that is already known to us is rather not computationally efficient. It is like cutting a birthday cake with rather some sort of a huge machete. So it is something of that sort. So just because we have sophisticated resources, it doesn't mean that we have to every time involve it. So there needs to be efficiency associated with whatever technique that we are adopting. So that is one critical aspect of the theoretical material research. So we need to not only use a right technique, but we also need to use an efficient one. There is always there is a need to be being efficient and being accurate. So there needs to be an balance between these two aspects. Like if you do some DFT calculation, you would have already experienced identifying parameters that arrive or that gives us the right balance between the accuracy and the computational efficiency. So okay. Now, so therefore, instead of having or adopting machine learning techniques, even regression techniques for estimating or for extracting a function from these different data points, what essentially is done is the expression for the expected expression for the free energy function, that is the parabolic function, is written. So the expected expression for the parabolic functions, let us assume that we are now considering a binary system, would be of this form. So the expected function can be written like this. So we have the C, that is the variable, the concentration, and we have A, B, and D. So these are coefficients, and when you are able to identify or accurately estimate these coefficients, you will be able, using this function, to appropriately fit a parabola through these individual data points. So what CalFAT gives us is the individual data points. It gives us the individual data points. And now using these data points, if we are able to identify, so these are the ones in the green is what CalFAT gives us. You feed in the concentration, it gives you the corresponding free energy and the chemical potential. Now using these data points, if we are able to derive these coefficients, that is A, B, and D, what essentially you will be able to do is you will be able to fit the curve for these individual data points. What we mean by fitting the curve for these individual data points is you will be able to arrive at an expression for these individual data points. Now, how does this all relate to rather identifying the derivative of these data points? Now, when you consider this function here, now you have this function here, you have this purely theoretical function here, all that you know is some concentration values, or you know some concentration and the free energy corresponding to that concentration is known to you. Say for instance, you have 5 data points, you have 5 concentration values, and corresponding to that 5 concentration value, you have say 5 free energy values. Now, using these points, you need to rather derive a function that can be used in the numerical model. Now, when you have in such a condition, and since from the nature of the plot, since as a metallurgist, as someone who has already dealt with the thermodynamics of materials, we know that there is a parabolic function. So this particular points, they follow a parabolic trend, and of course even by just looking at it you can see that it follows a parabolic trend, and therefore we approximate it. So this is rather an assumption. So we say that since it is of a parabolic form, we are using this expression as a starting point. Now when you take the first derivative of this function f prime of x, what you would end up having is 2ac plus b. So when you take the first derivative, you have this expression 2ac plus b, where c is the variable. Now when you take the second derivative of this function, what you would end up having is 2a. So what essentially we have is, we have a function, we assume that from the nature of the curve, we assume that this curve can be represented by, or this curve can be rather accurately represented by this function here. And we took the first derivative of it, one of the coefficient vanished. We took the second derivative of it, the second coefficient also vanished, and all we are left is with one coefficient and the second derivative of this particular function, this function that we don't know. Now, if we are able to find the second derivative of this function, then what we can do is we can find the value for one of the coefficient. If we are able to find the second derivative of the function that we already don't know, we will be able to find one of the coefficients. Now, even though we don't know the function, we have the set of data points. We have the set of data points, that is, we have concentration 1 and the corresponding free energy for the concentration 2 and the corresponding free energy for the second, so on and so forth, and we have concentration 5 and the corresponding free energy. Now we have set of data points, and in the previous lecture we saw how the approximation techniques can be adopted to find the derivatives of these data points, and now that approximation techniques can be extended to find the second derivative of this data point. So we know the approximation techniques can be adapted to find the derivative of this data points, and so even though we saw in our last lecture the first derivative of this, of course it can be extended to the second derivative, and when you extend the approximation technique to the second derivative and then adapt it to handle these set of data points, what you will essentially be able to find is the second derivative of these data points. And when you find the second derivative of these data points, it is nothing but twice the coefficient a. And now just by considering the second derivative of the data points, you are able to identify one of the coefficients. Now this coefficient is now known, and you can substitute it in this expression here, and you already know the the first derivative. So you will be able to calculate the first derivative of this data point. This is something that we saw in the previous lecture. You will be able to handle this set of points in such a way that you are able to estimate the first derivative and substitute a known concentration, because these are individual points, the concentration is known. So it is possible for us to substitute the known concentration. So is known, A is known, the concentration, these are correspond to the individual data points, and you can choose one of the concentration and you will be then able to solve. The derivative is known, and substituting one of the concentration, you will be able to have the left hand side of the equation a specific value, and the A is estimated from the second derivative, and thereby what you will also be able to then identify is the B as well. And finally, again, we know what A is, we know what B is, we can choose a specific concentration, and what you will be able to do is, and we will be able to find the corresponding, choose a specific concentration, meaning we can choose one of the known concentration and the known free energy. We can choose one of the known concentration and the known free energy. Then you will also know the left hand side of your expression, and ultimately then in that case you will be able to identify the third derivative as well, or rather third coefficient as well. So what we have is, we just have set of data points, we have set of 5 points, and from that 5 points we attempt to extract an expression that can be used in the model. So this expression, it rather reflects the relation between the concentration and free energy. Now in order to do that, what we have done is, from these data points we attempted to find the first derivative of the data point, the second derivative of the data point. The second derivative of the data points is independent of the concentration, so using the second derivative of the data points we are able to find one of the coefficient that is required for our approximation, and then we consider the first derivative, feed in some known data points. So these are the known data points, feed in some known data points, and using that we are able to estimate the second coefficient that helps us in approximation. Now finally, feeding in or considering some known concentration and feeding in these two coefficients, we are also able to identify the third coefficient as well. Now essentially what we have done is, the ability for us to find the derivative of a given set of function has allowed us to approximate a parabolic curve, and this parabolic curve can either be fed in or can rather be included in the numerical model and the individual. So once, so supposing we have considered just 5 points, and for your information, this technique is referred to as the 5-point tensile scheme. So when you have 5 points and you want to find the derivative of these 5 points, what you can do is you can adapt the 5-point tensile scheme. So this is 5-point tensile scheme, and this scheme can be adopted to efficiently identify the second and first derivative of course even higher order derivative of a given set of 5 points. So just with the help of 5 points alone, what you are essentially able to do is, you are essentially able to approximate this curve here. So what you are doing before developing your model, before using your model, you are focusing on 5 different points, and for this 5 different points, using CalFAD, you are estimating the corresponding free energy values. So you have identified 5 different points. So this is point 1, 2, and so on and so forth, and using CalFAD you have identified the corresponding free energy values, and by combination of these two you develop this data set, and using this data set, by considering or by solving for the second and first derivative of this data set, you have now approximated this black line based on this 5 distinct points that you have initially considered, and you have developed this function. Now this function will give you the information about the required information about the unknown data points. It will give you the information, the free energy information about the data points that were previously unknown. These data points, this one, any point, any concentration, this curve would give you the required information about the free energy information and also the corresponding chemical potential information. So once you have the expression, now where the A, B, C, A, B, B, the coefficients are known. Now you can substitute any concentration, and then you will be able to get the corresponding free energy. You don't have to exchange any information from when you have this function. You are able to use, or you are able to gather the free energy for any concentration. In the same way, chemical potential, all you need to do is, for the chemical potential, you need to take the derivative of this function. It will be of this form, and since A and B, the coefficients are already known, all you need to do is feed in the appropriate concentration, then you are able to identify the chemical potential. So what we have done is, so the state-of-the-art techniques are there, wherein they run parallelly in order to ensure that we have quantitative model, wherein they have, so in order to achieve this quantitative modeling, they run parallelly two different packages. You have your model that is running, the numerical model that is running. On the other hand, you have your thermodynamic model that is running. So they are exchanging information in order to make your model quantitative. On the other hand, whatever we have learned now, just finding the derivative of a set of data points have helped us to rather make the whole approach efficient. All that we have done is, instead of running two different packages, we have now introduced a function, and using this function now we are able to determine the required information of free energy and chemical potential. So this is how the relevance of, or this is what the relevance of identifying the derivative of the set of function is in the materials research. So this is one of the rather prominent relevance. So just our introductory lecture, or just few lectures in this particular course, or just a fundamental understanding of how to find the derivative of a set of functions or set of data points has helped us rather make a quantitative model more efficient. So this is the reason why at times we need to find the derivative of a set of data points. It helps us achieve, in this instance, since the resulting function, we have an idea of the resulting function, so this has helped us achieve or translate the discrete points into a function. Now, of course, with this, I would like to rather wind our discussion on the identifying or solving the derivatives in a numerical framework or using a computational device. Of course, even though we have restricted our discussion to finite difference, so there are different other schemes that can be used for solving our derivative using a computing device. Now, the understanding that we have gained, of course, we don't have enough time to look into each and every scheme that are available for us to solve the derivatives. The understanding that you have gained from the central difference would be helpful for when you explore yourself the different techniques. It will rather be helpful to understand what these different techniques entail. So what essentially we will be doing in next lecture is, we will be considering how these numerical techniques can be adapted to handle integration. So far we have largely been confining ourselves to derivatives, differentiation, and we have focused on the finite difference scheme. So understanding this scheme would help us look into the different approaches that are there to handle the derivative of the function. Now what essentially we will be doing, we will be winding up our discussion on the derivatives, and from the next lecture onward we will be looking into how we can use these numerical approximation techniques to solve integration. Goodbye. We will see ourselves in the next lecture, and we start with integration. Goodbye.